اوكي، مساء الخير اعزائي، ارحب بكم بندوه الكندي لهذا اليوم عن صناعه اشباه الموصلات. الندوه هي بالحقيقه اخر ندوات البرنامج الشتوي لجمعيه الكندي للمهندسين بالمملكه المتحده. البرنامج الصيفي والربيعي راح يعلن بالمرحله القادمه ان شاء الله خلال الاسابيع القادمه. المحاضره اليوم هي مثل ما قلت عن صناعه اشباه الموصلات، يلقيها لنا الدكتور علاء العاني. I would like to give a brief biography about Dr. Ala Al-Ani. Dr. Ala Al-Ani is a principal engineering consultant working in the field of semiconductors. He graduated with a BSc degree in control and system engineering from University of Technology in Baghdad. He holds a PhD degree in digital system testing from Brunel University, UK. He is a member of the Institute of Engineering and Technology, IET, and has been chartered engineer since 1994. He published numerous papers in international conferences and journals. He also holds 2 international patents on integrated circuit testing registered in the United States. Dr. Al-Ani worked as a research fellow at Brunel University following his postgraduate studies, and then joined the LSI Logic from 1994 to 2003. And work as a principal design engineer at Imagination Technologies from 2003 to 2017. He's currently a principal engineering consultant at Sandrail Limited and the director of Light Technology Limited, a UK-based private company specialized in engineering training and technology transfer. Dr. Al-Ani joined al-kindi Society of Engineers in 2005 and has been a member of executive committee and is former chairman of the society. راح اتمنى لكم انه المحاضره انه تستمتعون بالمحاضره، ان شاء الله تكون محاضره يعني قيمه، اتمنى ان تنال رضاكم. عندنا بس ملاحظه بالنسبه للمحاضره، راح تكون بحدود 45 دقيقه. الاسئله والاجوبه راح تكون بنهايه المحاضره بحدود 25 دقيقه. الاسئله في حاله هنالك اي سؤال خلال المحاضره يرجى يعني تركها لنهايه الكلام الدكتور علاء. ممكن كتابتها عن طريق الشات، او ممكن بعد انتهاء البرزنتيشن مع الدكتور علاء ممكن just raise your hand and we'll take the question يعني sequentially. ارحب بكم مره ثانيه واتمنى لكم محاضره ممتعه. اترك المايك للدكتور علاء، واتمنى اذا توضعون الميكروفون على وضع الميوت عندما يبدي الدكتور علاء بالمحاضره. شكرا جزيلا لكم وتحياتي لكم. تفضل عزيزي الدكتور علاء اذا ممكن.
Okay, thank you. Just to repeat what Kadam just said, I'll do the presentation, which will take about 40-45 minutes, and then followed by a Q&A session. So if you have any questions, you could raise your hand towards the end of the presentation, or you just ask your question on the chat if you like, or if you prefer to wait until the end and then you take part in an interactive session after the end of the presentation. I welcome you all in this evening, in this presentation. Let me share my screen. Okay, welcome all, and hopefully it will go smooth to this presentation. I'm going to talk about the semiconductor industry in general. I chose a subtitle which is like "From a Grain of Sand, Technology Emerges," and this is a fact because all semiconductor starts from a grain of sand, and we are going to explain this later on. This presentation or webinar will be talking about this industry, but actually I gave some of my talk 2 years ago at Salam House in London about the 4th Industrial Revolution at the time, and you could find it on YouTube. But this is slightly different or more focused on the semiconductor in particular. History and evolution. The agenda will consist of a number of aspects. First, I'll go quickly through the history and evolution, then for Industrial Revolution. I'll just talk briefly about the stages it has gone through until reaching this, and then advances in electronic, and then I dig deeper into the semiconductor industry, covering design, flow, manufacturing. I'll give some microprocessor examples just to see the scale of these, the complexity of these chips, and then I'll show you a couple of examples on supercomputers and what they could do, and then move to the global semiconductor market, talking about different geographies and countries and so on. And then I'll take some examples that from developing world, maybe you could consider that. And then we move to the Middle East, and then we finish with the challenges and opportunities in this sector, in particular to developing countries, and what opportunities are there if they invest in this sector. At the end of my presentation, there will be a Q&A session. My colleague Kadum, the host, will organize that. Okay, and we'll give it like about maybe half an hour or 20 minutes. It's up to you, Kadum. History and evolution. So when has it all started? It all started in the 1760 to 18th, so it's like 16th century to mid 17th century. It started by mechanization, where the industry started to use machines rather than manual. So it replaced manual manufacturing. And the iron is a fundamental element that has been used or started to being used in production. The steam power enabled, like massive power to be in the industry rather than manual and some simple means of moving and operating machines. So, and then the chemical manufacturing started as well in that era. Great Britain was one of the leaders, actually, as the leader at that time, leading other countries during this or through the first industrial revolution. The second one is in the 19th century, 1830, 1850, and so on. It started with rapid industrialization, where lots of industries have emerged in different sectors of industry, and then production technology started, where the slightly mass production started rather than small scale. What enabled that was the electric power invention and the generation of electric power, which enabled lots of machines and mechanization to be actually more effective and faster, moving at faster pace. The telegraph, which enabled the communication or first form of communication in that era, and then what helped actually for especially in transporting manufactured goods and raw material is the railroads, and that transportation facilitated that growth. And the third stage of the Industrial Revolution was in the 1950s to 1970s. Shall I say that some of us witnessed that, or some forms of that, without showing my age. The digitalization, which moved from the electrical to electronic, or from the analog to digital, and the invention of microprocessors, computers, some communication technologies, and even robotics in simpler forms than what we witness right now. The information technology started in that period, some form of programming languages like BASIC, Fortran, and so on, if I remember well. Fortran started in the 60s. And then, you know, for trade and commerce, COBOL was one of the languages and so on. So that has changed since the 1980s till now. And we are actually witnessing the birth of the fourth industrial revolution now, where a mix of sciences, electricity, communication, information technology, programming, artificial intelligence, automotive, and so on, they're all fused together in order to create advanced gadgets, equipment, technology, and so on. So it's a mix of science and technology, including mathematics, physics, mechanics, mechatronics, a lot of more, many more disciplines. Robotics is gaining very highly on the agenda, and lots of investment in that sector. It's going on now. And then the artificial intelligence. Artificial intelligence is not a new field of science. We've studied it a long time ago, but it used to be like more theoretical about very sophisticated, special and specialized algorithms with very small applications. Now that has widened up. AI is being used everywhere. And we could have some examples in medicine, in not just education, in self-driving cars, etc. Deep learning is another thing that is gaining momentum now, and the Internet of Things and the cloud computing. The Internet of Things, we could see this figure where all equipment are becoming smart and can communicate, take order, and execute certain instructions, whether it's like a freezer in your house or your car, or a laptop that's far away from you, a computer at work while you're sitting at home, or even your coffee machine. Smart homes like lighting, humidity control from a distance, and everything else. So all connected through the Internet of Things, which is like a means of connection and actuating or actuators to execute. Also, the cloud computing is another field that has emerged recently because it's the size of the data that need to be exchanged. So if you exchange the data size that you need to use. So if the data or the software that cannot be installed locally because of limitations, then you could use the cloud, and your software, your data, your database, your system can sit somewhere else far away, thousands of kilometers from you. And data centers, you don't know where they are, but it's quite secure, and you don't have to worry about it. So this is another way of dealing. All these disciplines are enabling lots of impressive and fast-moving technologies and inventions human beings are enjoying, and lots of us, are interested in that. We have seen how cars can park themselves now, for example. That was inconceivable 30 years ago, 20 years ago even. So these are the advantages. So what is enabling this? The fundamental brick or foundation for enabling all these is the electronic devices. I could say, it's software plus hardware, but if we see the electronics, what has been moving fast at a fast space, enabling all these technologies to exist and to emerge. So this slide shows you the electronic devices and the computers. Above the line are the devices, how they evolved since 1920s. For example, some people have seen these tubes. All TV sets used to be full of these, at least like 12 or 15 or 16. I've seen one. And the computers are very limited in terms of computation or computing power. But they used to occupy huge space, like a tennis court, for example, something like that. And then when we moved to 1940s, started getting these tubes into transistors, amplifiers, and other discrete devices, where the computer started being much smaller, much smaller in the 60s, although this is like just a word processor and so on. And then moving to the 80s, these devices have become more integrated into chips. So the chip might, for example, might include hundreds of these devices, but reduced in size, and at the same time, it's becoming faster and faster. So the computer has moved as well in a similar pace, and moving forward since the turn of the millennium, we have started seeing highly integrated microprocessors, very powerful, that allows not just like personal computers, but allows lots of equipment to operate at fast speed with much high compute power. Now we could see a single board computer. So if you look at this picture right to the left, the bottom left corner, the computer and so many people are there. You could see the size of the cabinets, and now you could see a single board computer, maybe 100 times more powerful than that one, in a like 20 by 20 or 30 by 30 centimeter, or maybe even smaller. Now, that was my fourth industrial revolution, how it evolved, and the back of some background in history. The semiconductor in Arabic is ashbah al-muwassalat. Why we call it semiconductor? Because it conducts sometimes and doesn't conduct sometimes. If you need it to conduct, you have to apply some voltage, right? As simple as that, just to oversimplify. So where does it start? It starts with a concept. A concept could be like somebody sitting on a chair and in the living room and says, let me think about making a phone or certain equipment or something does, you know, anything. So it's just a concept, but how you translate it? You translate it through a long process, which is very well structured. You draw a block diagram, architecture. It's like a building, for example. You start with architecture, and probably if you want to build a hotel, how many rooms, kitchen, swimming pool, lobby, etc., and so on. And then you design. The design will translate the architecture into more detailed specification, and then synthesis. The synthesis, sorry, I need to go back. The synthesis is it translates the design or the block diagram into real logic gates, which will be translated at the layout stage into physical drawing that resembles what we're gonna get on silicon, and then it goes through manufacturing, After manufacturing, it's subject to test and packaging. We package it, whether it's ceramic, plastic, etc. And then we assemble these parts or integrated circuits into on boards. And then we get the final product. So we all are familiar with block diagrams in architecture, whether it's like related to semiconductor or anything else. A block diagram is a block diagram. There's a number of blocks connected with arrows or by arrows in order to indicate or illustrate the data flow and the control as well. So if you look at the vertical double arrow or double-sided arrow, abstraction and implementation. So as you go up, this is like high level, very abstract specification. And you could translate that into behavioral model using C language or C++ or System C as we use. From that model, you could, with the refinement and translation, you get something like RTL model, which is register transfer language, or VHDL or Verilog. These are the three most widely used three hardware description language in the world. So some people prefer Verilog, some people prefer VHDL, but they could translate one to another. Translators are available. So you get the RTL spec in that, and then you synthesize and you get a circuit, whether you implement this as a FPGA prototype, which is an easier flow, or you get ASICs out of it, which is application-specific integrated circuits. And then you subject that to lots of verification in order to, during implementation, in order to make sure that what you get is what you have specified in the first place. Now, this is, for example, more detailed example about a mobile phone. You get DC-DC charger, you get wireless charging, you have the buses in between, frequency control, you have discrete components, logic gates, etc. You got HDMI interface, for example, camera, etc. It could be, you could use it as that is more detailed, but it doesn't tell you anything about the implementation. So you're still high level, abstract, but you're putting more detail in your design. So when it comes to design, we translate that into more details even further. Like we start talking about instruction registers, some logic gates, multiplexers, arithmetic logic units, accumulator, decoder, etc., without telling what the decoder is, without telling anything about the accumulator. And there's a memory, so you write into the memory, you read, and you address, you've got address, you have to specify that. So this is like CPU, a typical CPU in the computer, what it consists of. Now we synthesize. Well, how do you translate that block diagram, for example, into logic gates? We haven't really touched anything physical yet. We're just like modeling. This is all modeling and design on paper or virtual, let's say, logic. So when we synthesize, we use libraries. Libraries come from manufacturers. They say, if you have this model, RTL model, then we could synthesize it. You could get some logic gates out of it. So for example, this is very, very simple example. The output here is the inversion of A and B, which is A and B, or inverted C, because this is the inverter. So C gets inverted. So here you get that. And D, which is D. D you could consider it as enabled. So for example, no D, no output, because it's AND gate here. So whatever you get here, you get inverted there, and you get the final results out of this. So the synthesis is translating this language, programming language or model, into logic gates. So translate these gates into layout so that we can build this integrated circuit. We translate it into layout. The layout of an inverter, for example, you could see this inverter on this one or this one. Whatever gets here, it gets the opposite of the output. So it inverts. So this is, for example, one example of in-out. Whatever you apply here, you get the opposite there. So you apply 0, you get 1. You apply 1, you get 0. As simple as that. This is a drain, that's a source, and this is the gate. This is the output. So these are various gates, simple logic gates. We have a model for the NOT inverter, for the AND, for all logic gates, exclusible, or NAND, and etc. So once you get that, you get a drawing that can be implemented as it is. So we take a picture of this circuit, we translate that on silicon. So this is one example. You know, we translated the previous slide into thousands of gates, or maybe millions of gates. It depends on the size. So for example, this is 270 micron by 200 micron. So it's like 0.2 millimeter height, and the width is 0.27 millimeter. We put it together, all together, in order to connect it to get something useful out of that. And the chip can maybe consist of multiple of these, maybe 10 or 15 or even 100 of these. But this is just one example. So manufacturing, we translate the picture in the previous slide into a tiny, chip here. Each one of them is a chip. These they sit on wafers, and they're supported by membrane. And we produce in each wafer hundreds of them, if not thousands. It depends on how big each one of them. So you take each one of the microchips and subject it to some test. Test is very, very precise process. You get laser probers, wafer probers. They test each one of them, or you could program it so that you could test samples of them. So like few on the edge, few at the center, few around the center, and so on. It depends on how you program it, how rigorous your test is, or how reliable you want, your output. So packaging, for example, these are some of the packages. Example, this is the chip actually sitting in this biggest structure, which is the package. This is the back side or the top side. That's the another example. This is probably the other side. But then you take each one of the packaged parts, you assemble it on boards in order to make final boards, whether it's a motherboard, whether it's a TV decoder, whether it's a digital radio or a mobile phone. You get the final product. For example, this is a I think it's a Samsung mobile phone. You could see that Samsung flash memory and the processor from Samsung, but they also use other integrated circuits from Cirrus Logic, from Avago, from Murata. They do some small components, and Fairchild. Fairchild used to be very, very famous companies in the 80s, but not anymore. But you could see that most of the components or the integrated circuits are manufactured by Samsung, but other vital components come from different companies. This is the backside of it, because this is a PCB or the board is double-sided, so they use maximum, space. So they do double-sided, and they mount integrated circuits on the backside as well. So we've gone through the flow until from concept till final product. We are going to now dig deeper into the manufacturing process. That's why it's highlighted with a lovely pink. How does it start? Step one, you get a grain of sand. It's you call it silica sand or silicon dioxide. They mix it with carbon and remove the oxygen at very high temperature, and then treat with oxygen to purify to 99%. 99% is not good enough for as a purity. You need more pure or silica or glass, and then you grind it. You grind the 99% pure glass into or silicon into fine powder to get rid of, and then you treat it with hydrogen chloride and so on. You subject it to high temperature, 300 centigrade, in order to get, and you distill it in order to get 99 and 6 nines after the digit, after the decimal point. So once you get that, you move to step 2, purify from polycrystalline, because polycrystalline get formed structure within the silicon, and then you melt the silicon crystals in a quartz crucible at 1400 centigrade, and then it becomes really very liquidy, and then you dip a tiny crystal into the molten silicon. It becomes like a seed to attract the silicon around it. While you spin it, you form, or you get the spherical or cylinder or pure silicon, 300 millimeter across. Some factories try to go over that to 450. In the past, it used to be 150 or 200, but then advances in technology have allowed that to become 300 millimeters. And some companies tried 450, but it hasn't become very popular. I don't know, because maybe it's really hard, and throughput is not brilliant. Step 3, you cut this cylinder into small discs, tiny, not tiny, sorry, thin slices. You slice it. Each one is about less than a millimeter thick, which is, I I don't know why 775, but it is like 31 mil. And those who are familiar with the inch, you know, they know the mil is 1/1000 of an inch. So 775 micron is about 0.775 millimeter. And then you lap it, and means you polish it, you get some of the ripple or uneven surface, and then you treat it with acid to make smoother surface. And you get wafers, that's what we call them, very shiny, you know, discs that are very fragile. Heat up, the next step is to heat up the silicon wafers to create silicon dioxide and then make patterns using photoresist chemicals. Photoresist chemicals, just like the old photography, is very similar. You know, the layout we talked about, you know, it's just like they put a photoresist on it, and then they subject it to UV light to print the circuit drawing on each one of these chips. And then you expose it to UV light through a photographic mask. And then you move the wafers step by step in order to print them, to print all the chips on that wafer. And it's subjected to lots of chemicals, polishing, etc. And these are very complicated, very slow processes, and so on. And actually, one YouTube I watched on by Siemens, I think, yeah, video on their fab. They say in order to get this, you go through about 12 to 1400 steps. So it's about 1,400 steps in order to get the final wafer. So let's dig deep into the transistor. The fundamental building of transistor is called MOSFET, which is metal oxide semiconductor field effect transistor. MOSFET, or MOS technology, in short, are basically switches. So this is a switch. This is the drain, that's the source. This is the gate. You apply voltage here. The drain can contact or conduct current from this end to that end. As simple as that, without going into detail. And the wafer is blasted with boron ions, blocked by photoresist layer to direct the beam to precise location, create a P well. So you create a P well, you create an N. This is the P substrate. These are the N wells. A similar process using phosphorus ions is just like slightly different material to create the N. And then these wells are called drain and source, as they call them here, drain and source. Right. Okay, transistors need a gate. So you basically an electrode covered or coated by a thin layer of metal oxide in the middle to form a gate. And they connect the drain and the source in order to create that switch. In order to reduce the size of the transistor, because the whole industry is thriving, is all they obsessed with how to get the transistor smaller, how to make it smaller, how to make it faster. There are three factors: smaller, faster, lower power. That's it. That's all the whole industry is moving to achieve these goals. And that's how technology progressed over the years. Intel, for example, instead of like a single layer, they did FinFET. That allowed drop. This is a 3D gate. So the gate has actually got many fins, very similar to the shape of the fin of a fish, and they allowed to shrink the transistor from 90 nanometer to 22. So they almost 1/4. 1 nanometer is 1/1,000,000th of a millimeter, of course. So you can imagine how small it is. And billions of transistors on the wafer are formed. And you look at the wafer, typical one, look at that, drain, source, and gate. Each one is a transistor, and this is a dummy gate. So what do we get? And next step is transistors are just the basic or the bottom layer. They need to be connected. So these are the transistors, the tiny structures down there. And then you connect them through metal layers. These are copper wires or other metal they use. You connect the transistors through sources, gates, etc., supplies, signals, and so on. And you need to, because these are tiny and very densely rooted, so you need multiple layers in order to take some of the signals out of the chip at the top layer. So this example is metal layer 1, 2, 3, 4, 5, 6, 7 layers. We're dealing with 11 or 12 layers nowadays. It's quite popular because transistor is shrinking. Such a incredibly complex process is prone to potential problems. Of course, we are dealing with nanometers, any impurity, any dust, any inaccuracy tolerance would be devastating, or will create big problems and then impact the yield. So a typical yield from wafer, for example, is around 80. Some of the mature technologies, they could push it to 90, 95, but this is very rare, especially at different corners because, different temperature, different voltages, and so on, they compromise the yield. So this is a wafer. The ones that have been removed automatically by a robot are the defected ones. So they just remove them completely, leaving the good ones on the wafers. They tested using wafer probes, as I showed you earlier. And then wafers are sliced into individual chips and sent for packaging. Packages provide strength and protect fragile dies. These are very fragile. I'm going to show you, I have got some samples after the presentation before the Q&A. I'll show you real examples of wafers because I've got 3 wafers at home. And I'm quite keen to show you because it clear up the picture, I think. So why we package them? We package them because they are very fragile and they are prone to dust, heat, temperature, pollution, anything, impurity, scratch, oxidation, and so on. So we need to package them. Packaging them is encapsulating each one of them inside it and close it around, from all sides, using either ceramic, plastic, or metal. It depends on which sort of package you use. Package dies are soldered down on printed circuit boards, as we've seen, used in computers, mobile phones, etc. So this is an example of one of the boards. Microprocessor examples. We have two. I included in this presentation 2 examples. One is the Zen 2 by AMD. Is a processor manufactured by TSMC, which is Taiwan Semiconductor company, using 7 nanometer FinFET. The one invented by Intel, as I mentioned, and it has 39.54 billion transistors. Okay, this is not a single chip. It's 8 dies packaged in one substrate. So it's a combined die. So basically, that's how it achieves that integration level. The other example is the Apple M1 used in their computer. It has 8 cores CPU, so each core can actually, they could share the compute power between them. And it uses TSMC again, 5 nanometer FinFET, 16 billion transistors, and the neural network, 11 trillion transactions per second. This is suitable for neural networks, which requires very fast processing. So these are the microprocessors. We could create supercomputers out of the microprocessors by multiplying these processors and use thousands or hundreds of thousands of them. So one example is the Summit. Summit is a US Department of Energy. Use it. I mean, you could see this is like an Amazon sort of warehouse with full of cabinets. And it needs its own power supply, and it consumes huge power just to cool it down. Because, I mean, imagine each cabinet contains thousands of processors, each one emits heat. So how many cores? Each core or each processor is, like IBM Power 9, that's what they use. 2 million, 2.2 million, 2.3 million, in the computer. And on top of that, they use about 2 million NVIDIA cores for graphics and video and all that to help the main cores. And then the peak performance is 187.66 petaflops. Peta is the 10 to the power 15. And the flops is floating point operation per second. So you can imagine, what speed, what they can do. And that's what they measure, how they measure the efficiency of it. So 11.3 gigaflops per watt. So just to keep the power down. Another example is the Chinese example, and Tianhe, if I pronounce it well. 2A is the Milky Way, China National University of Defense, and you could see this big site, and it similarly has 5 million Intel Xenon and matrix of 2,000 cores. They don't know the exact number, but it's around 5 million. Peak performance is 61 petaflops. Well, that one is 187 petaflops. And it's in terms of power, 3.3 gigaflops per watt. So that's what we could do with microprocessors with silicon. And I think we talked enough about the technology. I hope I explained well the stages to where it starts, semiconductor, where it ends, and the main applications of that, how it evolves, evolved over the years. Now, if we move to the market, wafer fabs. Wafer fabs is a shorthand for fabrication plant or fabrication, factory. TSMC is the Taiwan Semiconductor Manufacturing Corporation. It produces 28% of all semiconductor wafers in the world. If you look at Taiwan, is a tiny dot next to China. You could hardly see it on the map. They produce 28% of the global production of semiconductors, and the company is worth $47 billion. UMC is another Taiwanese, United Manufacturing Corporation. It produces 13%. Samsung, it produces 11%. Samsung is much more known because of the mobile phone, not because of its manufacturing capability. And the SMIC is the Chinese semiconductor, is 10%. Global Foundries is, you remember this name, Global Foundries, I'll mention it later, is 7% because it's something related to the Middle East, or connected to the Middle East. And then the X-Fab and Tower Jazz, they get like 3-2%, whatever, something like that. And there are small fabs here and there all over the world, in some other countries. So you could see the concentration or the distribution of silicon wafer fabs in the Far East and Southeast Asia, Indonesia as well. This is China, Taiwan here, Japan there. In Europe, small sort of capacity fabs. These are not huge. In the US, on the East Coast, Global Foundries, X-Fab, Tower Jazz, and TSMC. On the East and West Coast. We have a tiny few fabs here in Israel, but these are limited production. So this is the world distribution of the silicon or semiconductor industry manufacturing plants. Semiconductor manufacturing capacity by country. So you'll see that manufacturing has gone up. For 300 millimeters that I mentioned, which is like the diameter of the wafer, which is like most popular one. South Korea becomes highest, and then Taiwan, and then Japan, because some of the factories, they do it in South Korea. So it's not, South Korea is not just Samsung, it's other manufacturers. Taiwan, then Japan, US come fourth, then China. China might be exceeding the US, but now with Joe Biden's new initiative to recapture or resurrect the semiconductor and manufacturing or production in the US, it might push the US slightly ahead of China. And then Singapore, Europe, and Israel. Global market size. Semiconductor sales in 2020 is worth $439 billion. That's how big the market is. And you could see sales, for example, in billions in US dollars, is always going up. It might have some dips, here and there, but the trend is very strong, in the right direction, going up always. Now, if we look at the semiconductor from different angle, or try to digest that, or actually divide it into like different type of manufacturing or parts, then the industry segment, the equipment, EDA, design, foundry, manufacturing, and OSAT. The dark blue is China. Then the light blue is US. The rest of the world is medium blue. So you could see that China, in terms of equipment, they don't produce a lot. While, for example, in the design and and OSAT is the outsource assembly and test. So they do a lot of assembly and test, but they are not strong in the equipment or the electronic design automation, the software that allows us to do the design. So that one, so you've got the rest of the world is there, but the US is quite strong in this one, in the equipment they produce. In the software, they're dominating the world. And in the design, they're taking the lion's share as well. And in terms of foundry, no, they are not strong. And the assembly and test, they are not strong either. While the rest of the world, for example, Far East, Southeast Asia, look at the foundry. That's what we talked about, you know, Taiwan, Korea, Indonesia, Malaysia, whatever, the rest of it. Now, if we go to the fabless chip designers, these are design houses or design companies. They don't have fab. They don't have manufacturing. They just design it. And they ship it to a fab in Taiwan or in Korea to make the chip. So the US is the dark one, and Taiwan is always, the US is like lion's share here. And the overall revenue for the design in 2010, that was like 11 years ago, was $63.5 billion. And now it's gone to 84 in 2015. I don't have a figure for it in 2020, but it's over 100 billion. So the distribution is, you could see that the China and so on, you know. What's interesting here is that Japan is shrinking, you know, and is after what has been dominating the electronic or advanced electronic in the 70s, 80s, now is really playing a tiny role there. Very sophisticated industry, but very limited in terms of capacity. And this proves that, or because if you look at Japan, the bright blue line, in the 80s, they reached their peak, and in the 90s, they started going down, while South Asia in the 80s, they were tiny industry that is like going higher than anybody else, while North America has gone down, lost some of the market, and then tried to keep their position at one, you know, level. So as Europe, but Europe is not major player in the semiconductor manufacturing. This is another graph showing, you know, from 2000 and each one of these, showing like 2016 to 2022. This is, of course, predicted or estimated. But this is the EMEA. This is Europe and Middle East area, and then Americas, and then Asia Pacific. And you see that, you know, Asia Pacific is way ahead of Americas and the Middle East. So they are in the forefront or leader. Some of the countries, Malaysia, for example, export. This is just like random. I looked for figures in different countries to see what, you know, what the size of the market or what share they have in the electronic industry. So Malaysia exports 30 billion. That was in 2013. It hasn't improved a lot, but it's still around this figure or slightly more. Thailand as well, you know, it's valued like 100 billion, mainly automotive electronic parts. And the Philippines, only the shipment total 37, and 3 years ago, $37.5 billion. Singapore as well, valued at 37, something similar. Israel has got 5 fabs, small fabs, and then more than 15 fabless companies. They employ 20,000 people with annual revenue of about 5 billion. Okay, it's small compared to the Far East, but it's quite significant because Brazil, revenues from semiconductors just like $500 million 2 years ago. Brazil was just started with very good steps forward to establish themselves as a credible semiconductor player, but they struggled because they don't have the long-term vision, and you know, IBM and the rest of them, yeah, they lost interest in Brazil for various reasons. That's why it struggled to grow since its invention or started about 10 years ago. Now we come to the Middle East. There are some attempts to start a semiconductor, you know, industry in the Middle East, whether it's fabless or fabs, assembly houses, packaging, test, etc. So Silicon Oasis was established in Dubai back in 2001, and I have to say I contacted them when I heard about it, and I thought, you know, it might be a good idea for me to move to Dubai that time if they establish something like this. So I talked to the CEO, the manager, but he told me that you know, they have a grant for 3 years from the government. 1.25 of the year is gone already, and they've got less than 2 years left, and he wasn't sure about the future of it. So I changed my mind then. Yeah. So it was meant to be a Dubai oasis, or Silicon Oasis in Dubai, doing just the design, not manufacturing. They had about 12, 15 people there with managers and so on, and they were established in the something city. I think it's like IT city or technology city, something like that. Yeah. Abu Dhabi established advanced technology investment company called ATIC in 2008, which invested in AMD. AMD is one of the big players in microprocessor, as you all know. It's they compete with Intel. To create a global foundry. Global foundry, you remember what I said, you know, GF, global foundry, is because of the connection with the Middle East. Global foundry is 100% owned by Abu Dhabi since 2012. So it's been like 9 years. They actually own it wholly and completely. You know? And then another attempt in Masdar Institute of Science and Technology in Abu Dhabi collaborated with another company, with a global foundry, on this particular technology, 28 nano, to do low power CMOS technology and so on. And there is no news, no more detail about it, but I don't know what happened exactly, because they own it and they did end this internal program. If we come to Egypt, Egypt started technology startups well ahead of Abu Dhabi and Dubai in 1993. They actually discussed the idea with a French company called Anacan, I think one of the leaders or one of the veterans of this sector is called Hisham Hadara. I think my Egyptian colleagues probably know about him. He convinced Anakad to open a design center and office in Cairo. And then he, with Sameh Shaheen, joined forces, and two companies merged together in 2004. They call it Cyware. And then another example was a lady called Sahar Salim, CEO of startup Boost Valley. She started a company called Microchip, something called Boost Valley, is another design center. Currently, 17 fabless companies from semiconductor sector in Egypt. They do exist so far. I have no more detail about, the other activities that might exist in Egypt recently, but that's, I hope, our Egyptian colleagues can enlighten us on the latest. Excuse me, I moved ahead. Morocco. Morocco was the first Arab country to enter semiconductor industry established by ST Micro. ST Micro is a French / Italian company. They in 2003 they opened design center there. It was quite advanced and so on. They have access to all CAD tools and simulation tools used, and then in 2015 acquired by Sondrel, the company I work for currently. So we still own. They are part of us. Morocco in Rabat. There are about 45, 50 engineers and managers, and I have to say they're doing a brilliant job. Morocco manufactures and exports small devices, mainly optics and so on. For that period, Pneumatic, I think Pneumatic has ceased to exist now. But there is a packaging company called Masir in Rabat as well, doing electronic packaging. Now we are coming to see towards the end of my presentation. Sorry if I took longer time than expected. So challenges. What are the challenges? The challenge is not everybody can enter that market because of these challenges. First, the high capital. This industry is very sophisticated, and the equipment are very expensive. So it's not all countries can engage in that, basically because they cannot really raise that kind of capital. Because of the sophisticated science and complexity of the industry, lack of experienced engineers is playing a huge factor in limiting, countries from entering this sector. You need to train people for years and years. You give them access to the latest technology. They have to engage in long-term programs for technology transfer because nobody can invent it by themselves. And if they want to start from square one, it will take them like 100 years to catch up. So it's not practical. Long-term investment in R&D. It's not something that you invest today and you expect to see the results in 2 or 3 years' time, or even 5 years' time, or maybe, without exaggeration, in 10 years' time. you need to build it step by step. And you have to inject cash, money, investment, access to scientific material, patents, etc. You know, it starts from maybe secondary school or first year university. You change the higher education syllabus in order to give the students some practical and relevant experience. No good. You just like, you give them a couple of books, you say, go read these books and you'll understand. No, they will not understand. They will remember, you know, to answer the exams, but when it comes to, okay, can you design a small chip? They will not do it. They will not be able to do it. So the other point is that small national, regional markets, we need the ecosystem in order, even if I manufacture it in Egypt tomorrow, microchip, I need to sell it. I need to put it on a board. I need that board to come from a user. I need a market for that. I need a logistic, somebody to package it for me, somebody to test it for me. I cannot really do it all myself. I'm specialized in the manufacturing. So where is the ecosystem that? And where are the end products that will consume what I can produce or manufacture now? Finally, the lack of knowledge of global semiconductor markets needs. I mean, this is very related to the previous point about the small national regional markets. If you don't have clients, consumers, or end users locally, you have to open up to global markets. And you have to compete with the Koreans, you have to compete with the Malaysians, you have to compete with the Chinese, etc., to find your own market. This is a gap in the market I need to fill in because there are only few players and I could do what not many of them can do. This is the key differentiator. Now, opportunities. Why would you need to enter this market? It's quite lucrative. If I could say that it's one of few sectors that have not been affected by COVID-19 impact or lockdown is the semiconductor. It grew up a bit, even with this climate or conditions. So in terms of opportunities, economic growth and diversity, it feeds into the economic growth of the whole country because it feeds into different sectors as well. So for example, you could do the electronic, you could do, for example, small board that controls a washing machine or a dishwasher. Then if you could do that, it will feed into that washing machine manufacturing or factory to any electronic gadgets or equipment or appliances. Security, whether it's a military because it goes into radar, surveillance cameras, and so on, and something else like you know, tanks, weapons, anything. So if you can produce that, nobody can know the secret of what you produced. But if you buy it from somebody else, they know exactly what you bought. So they know your capability. Telecommunication is the same thing, another sector. Data, like you know, data centers, national security data security, national ID cards, health, NHS database, etc. And then intelligence, you know, spying on others or trying to counter attempts to, you know, other countries spying on you or espionage. And there are other sectors and examples we could draw. Highly rewarding jobs. I think, by just looking at the average salary of senior engineers and so on, they are quite, high, especially in the US, Far East. So they are above average, and not just the pay, it's just the feeling when you finish your product and you've worked on it for 18 months or 24 months as part of a team of 30 people, and then first thing you put it on the board and you test it and it works. It's just the joy is unbelievable. And then you creates local talents as well. So it feeds into like software engineering, assembly, test, all sorts of different sectors as well. And it absorbs graduates and feeds into other sectors. If you started this and you establish your industry in the electronic industry, it absorbs a lot of graduates, chemical engineers, mechanical, electrical engineering, telecom, robotics, you name it. And in addition to the vast number of managers and schedulers and so on, you might need. So thank you very much for your time and for listening. Probably we could start with the questions and comments, and I'll show you the samples before we start with that. So I'm going to stop sharing.
Okay, great. Thank you very much, Dr. Ala, for this insightful and excellent presentation. We'll start with the question from Dr. Mohammed Darwish.
Can I start before Dr. Mohammed? Sorry,
sure.
Dr. Mohammed. This is, I don't know, I wanted to show you this.
Yeah.
So this is one of the wafers, 300 millimeters.
Sorry, Doctor, the background, the blurry background motion you made. Yeah.
Sorry, I have to maybe show it like this.
If you put it closer, I think, yeah?
Yeah.
Wow, yeah, we can see.
So you could
like
see, yes, it's absolutely, but this is like about 900 or nearly 1,000. Let me just.
Yeah.
Yeah, can you see it? Or is it blurred?
It is a bit blurred, yeah.
At one point, I think it's just like.
Yes.
Is that better?
It is, yeah.
Yes. So you could see that about 1,000 dies or chips on this wafer, which is like 300 millimeter or 30 centimeter diameter, and it's just like it's supported by a membrane, a small one. They're all stuck on it. After the lockdown, if you're welcome to visit me to see it, and I'll give you a few free samples.
Okay. Definitely.
Yeah. The other thing I wanted to show you that some of the dyes, they come in small samples, not on wafers, and where is it? I think I put it in here. Yes. So I'm going to show you this. This is like small tray with 25 chips. One is missing. And they come into these packages. For example, this is a silicon. Let me just show my screen. So I could show you this. Yeah.
Yeah.
So you could see the top side, and this is the side way, and these are the pins that they sit on the board. I have very flat, very thin chips. These are imagination technologies that I worked on. This is a GPU, graphic processing unit. That's, I kept this as like this is 20 years old. Let me see if I could probably, if I put it next to my face, it will show. Yeah. And
yeah,
some of them are big, some of them are small. And what we could, you know, and the single board computer. This is a Raspberry Pi. I think some of you are quite familiar with that. This board is a complete computer. It has the power supply. It has the 2 USB connectors. It has the Ethernet cable. Even it has HDMI connector. And it's a very limited memory and so on, but you could connect it to a screen, keyboard, mouse, etc., and it becomes, you know, complete computer. The cost of this is about $40, and you could use it. There are plenty of programs, applications, and there is a huge group of techies, you know. They could tell you how to program it, how to use it for different applications. Thank you very much. I won't take any longer from your time, and we're open to Q&A.
Thank you again, Dr. Ala. The question number one from Dr. Mohammed Darwish, he's talking about asking about the raw material, the silica sand. The question is the silica sand especially a special type of sand which only exists in a particular part of the world? This is question number one. I will give you the rest of the question of Dr. Mohammed maybe. The other one is there any secretive part in this process, or it can be transferable to this knowledge to other countries? And the question number three, do we need to modify the education curriculum in Arabic countries, maybe from the primary school, to take part in this very competitive industry? So this is the question, please, Dr. Ala.
Right, okay. Yeah, thank you very much, Dr. Mohammed, for your questions. The sand is usually, they look for pure sand. And I don't know exactly what kind of, I haven't seen it, you know. We've got lots of sands in Iraq. Yeah, you've got a lot in Egypt as well. But I don't know, you know, how pure the sands in these countries are. But I read about it that they are quite selective in terms of, you know, what type of sand. It depends on the purity or how much impurity they have in it. In terms of technology transfer, yes. I mean, one way of doing it is to engage in a program, because there are lots of secret in this technology, and no one, you know, can just like jump in and you know, become or establish an industry. There are some fabs, they come in the market for sale. These are used fabs. They want to close down. From time to time, you hear about it, and these are small capacity, but like the one in the UK, for example, they closed a lot of them in the 90s and 2000, and you could buy it, and you could commission somebody to come and train your engineers, your technicians, and so on. It takes, you know, somebody who's got the money, the courage, they know what they want, you know, or a government that want to engage in this, so they could do it. Brand new fabs, very costly. At LSI Logic, we established one in 1998. It cost in Oregon, it cost $2.1 billion at that time. I heard recently that it costs between 9 and 12 billion for a brand new fab. Okay, education, yes, we start. Why not? Some of the secondary school students, they might engage and subject them to electronic design and so on. So you put it in the syllabus. At least they have the foundation by the time they go to university. They know how to design a small circuit. Thank you.
Thank you very much. We have another question from Ravinder. Sorry if I pronounced strongly the name. The question is belong to the reason of calling Silicon Valley. Is it that because of the electronic component used in this industry in the Silicon Valley, or because of the IT firms? I don't know if you have the answer for the question.
The name?
Yeah.
Silicon Valley. Well, okay. I've been to that part of California, south of San Francisco, about 25, 30 kilometers. There's nothing special about it, and no special sound, to be honest. It's all companies, but it's just a name.
I guess maybe the Silicon is belongs to the technology, or maybe is the basis for the technology there.
No,
so that's why they use the
that's
silicon.
why, yeah. That's where most of the companies are based. So you name it, and they have to be there because it has become a magnet for experience and talent. You know, and people from all around the world, you know. They travel there and they live there. Most of them, they live outside, but the companies, you name it, HP, Sun Micro, Intel, you know, IBM, all of them, Cisco, etc. They're all like roads next to each other and so on. Each one is you know, occupying large block, especially Cisco, for example, in the late 90s or beginning of 2001, 2. They created Cisco Village, which is like about 7 buildings next to each other, even a crash, you know, in a supermarket. So that's why.
Interesting. We have a question. Dr. Ali Sharbaz, he raised his hand. Dr. Ali Sharbaz, can you please?
Tafadhal, Dr. Ali. Unmute, please.
Yes, Dr. Ali. Great.
Thank you very much for the opportunity. Thanks, Dr. Ala, for the great talk. I had a dream when I was in Iraq to establish a fab factory in Iraq. Probably you shared that with me, Dr. Ala. But when I start to talk about invest in that later on, I found this is really it needs a government to intervene on that. And I remember we had in Iraq Al-Mansur, a company which manufactures some, probably you are better than me. Actually, my question is about why it's a certain part of the world, which is Far East, they dominate that. Is that because of the culture? Because I can see it's not a coincidence. I know you mentioned some challenges, but we talk about worldwide. It's all in the Far East. So from your experience, I feel there's something relevant to the culture. Yes, thank you, Dr. Alath. Sorry for taking longer. Thank you very much.
Very good question. Why the Far East? I think, you know, if you go before this, it was concentrated in Europe and in Americas. And then Japan actually started it in the Far East, way ahead of or before of China and the rest of them. So how they started as assembly houses and test, because the test, I could set up a test company now. I could give me a few millions I'll set up a test center. But manufacturing is very hard. So they all started as OSATs, outsourced assembly and test. So the big boys, the big players, they cannot really, they don't see more money in that. So they outsource it. Outsource it to what? To small companies, Chinese, Taiwanese, you know, and they started doing the assembly. Assembly is easier because you could get Samsung machines or from machines from My Data for pick and place, one PCB printer or two, and then an oven and a clean room. You could set it up. I gave Iraq, you know, a project because they asked if they wanted to do that, how much it costs and so on, and I gave them the specification how to do it about back in 2014, I think. Yeah, so it's quite doable. But then how to grow that business, how to sustain it, you need always, you know, to market yourself and to promote your business, to get attract more business from big companies so that you could sustain that, because these machines, they need to work continuously, not just like use it like, I don't know, like 3-4 hours a day. It's not worth it. They need to be working like 2 shifts at least, so 16 hours a day they work, because they are very expensive and you need to make, you know, money out of it. So why the Far East? I think they started with that. In Japan, I think, was leading the industry in that part of the world.
Thank you very much. Thanks, Dr. Ala.
You're welcome. Do you have other questions, Callum? Or? Okay, there are some comments about pure sands, I think, yes.
Oh, sorry, my microphone was on mute. Question from Karazan.
Yeah.
Yes, and he's asking about, is it right we have a lot of silica sand in the western part of Iraq? And I would like to add to that question as well, how much the raw material plays and impact this industry. Is it the raw material is a essential part of this industry? Because I can see, like, for example, South Asia is I don't think so they have except in China, I guess, these rare elements that is entered in these technologies. So can you please?
Well, yeah, thank you for the question. I would like to emphasize one fact, that the value of this industry is not in the raw material. Raw material, you could get it anywhere. If you don't have it, you could import it from neighboring countries. It's the know-how, it's the technology, it's the talent. So the asset, your big asset, is the skills and the knowledge. You create that. Raw material is not a big deal. You just need a long-term plan to establish this industry. You invest in the people, in the students, graduates. You give them the correct training. You know where to start. For example, I mentioned a couple of Egyptian veterans, you know, Hisham Hadara and Sameh. They established you know, semiconductor or silicon technology in Egypt from nothing, from scratch. I don't know how much support they got from the government, but I don't think, because it sounds like a private sector initiative. But because they worked somewhere else. That's what the Indians have done. The Indians have worked in the US, for example, for a long time. And when the US market went down in the turn of the century, most of them, they went back to India and established companies. Now we are using their talents and their engineers. And we are acquiring small companies. We acquired about, in my lifetime, about 5-6 companies there. You just buy them with the managers, with the senior engineers, with the engineers, and so on. And the selling engineers or companies, millions or hundreds of millions. So that's how you make money. And so it's not in the sound, it's in the brain.
Okay, thank you very much. We have a question from Hanan. She wants to know if there is any impact of cryptocurrency on the semiconductor industry, if any.
I haven't experienced that, and okay. I know very little about the cryptocurrency.
Okay.
Sorry.
Probably had a question from the booming of this industry that could be used more semiconductors. So I think it can apply to any new technology. It's going to raise the and affect the industry of semiconductor because they're going to use more semiconductors and hardware, let's say.
Yes.
I guess that.
I mean, one clear example is the car.
Exactly.
If you compare the cars 40 years ago or 30 years ago, you could hardly see any electronic apart from the radio and maybe signal when you signal, and that's it. Now the car of the future is going to be about like maybe more than 40-50%, electronic. And if I don't have a car, but now automotive companies coming to us to design microchips for them to do radars, long-range radars, short-range radars, LiDAR systems, deep penetrating cameras, all sorts of sensors and actuators, all artificial intelligence microchips in order to assess the situation in case of danger or high risk and so on. And the car is full of electronics. It's happening now. And you could see it in a couple of years' time. Most of the cars will be equipped with these, gadgets or electronic. Yeah.
Thank you very much. We have a question from Dr. Laith Al-Jabouri. How differ supercomputers from quantum computers based on semiconductor manufacturing?
I have a limited knowledge of the quantum computers and so on. I read a few articles, but I haven't really experienced that, and I haven't really worked on any project on that. So I don't know whether the audience can answer some of the or shed some lights on this question.
Okay, thank you very much. We have a question from Christos, which actually is a good question related to the pandemic, how he's asking about the current semiconductor shortage. How did the COVID affecting the supply of the semiconductors during the pandemic? Prices in computer components such as GPU and CPU increased, with even some automotive manufacturers, you just mentioned, automotive manufacturers not being able to source semiconductor for their vehicles.
Absolutely correct. That's a very good question. You are aware of the current situation. In the beginning of COVID-19, the first quarter last year, what happened is that some of the customers or most of the customers, they just put their projects on hold. If they haven't started, they delayed it. So the money is stopped, coming into the semiconductor sector briefly. What happened, that was reflected on the investment in terms of CAD tools, equipment, assembly lines, etc. And definitely hiring, recruitment. what happened then is that most of the companies, they realized that they need, this is like a temporary thing, and they need to start looking at especially high demand from laptop, tablets, computers, which was like really going down before COVID. And suddenly everybody started working from home. So they needed equipment. So the demand increased and the market, you know, grew again. And then the semiconductor, because they slowed down in their investment, their capacity did not grow. So there was a bottleneck. We could not really see any way out of this. Capacity is limited, and we have the demand. On top of that, the demand came from automotive. All car manufacturers, they started coming to us, you know, saying, we've got this chip, we need to make it. And so anticipating what the market is going to be and the demand in the near future. So there is a bottleneck in manufacturing. Manufacturers have to plan way ahead in order to rise to the demand and to meet the demand. So what happened is that, for example, the time at the factory has increased. The assembly and packaging has doubled. So I used to have for packaging, for example, 8 to 9 weeks lead time for package manufacturing. Now it's taking 20 to 24 weeks. So when negotiating, we are paying high premium in order just to reduce it. That's what the situation is. But this will change. We'll go back to normal gradually starting 2022.
Okay, thank you. We have a question from Hussam Jafar. Do you think ARM will take over x86 architecture in the data center in coming years?
Yes.
Okay, great.
I think so.
Okay.
Yeah, because their performance is really improving.
Okay.
And ARM is one of few companies in the world that they have impressive history. I know ARM since they were in Maidenhead and started open, you know, design center in Cambridge. But the business model they used is very remarkable. It's very impressive. They penetrated all markets. And working for Imagination Technologies, myself, specializing in GPUs, they did not have a GPU, they have a CPU. But then they started competing with Imagination, the other player, you know, in the GPU market as well, you know. So they grabbed some of the customers, you know, from them. And they're everywhere. ARM is everywhere. All gadgets, they have ARM processors. They have got like small, tiny, low power, very cheap to very powerful, high performance, big and so on, processors. So they cater for different segments of the market. And this is a clever bit.
And I think the power consumption for ARM claiming they less power consumption structure or architect, maybe that's going to be very useful in the data centers.
Yes, of course. I mean, power is a big player, a big factor.
True. Yeah.
Everything. Yeah. I mean, if you take like mobile phones, for example, any portable equipment, as well as the data center, because data center, if you could make a saving of 2% in the processor power or consumption of the processor, and you multiply that by 2 million, right? You could see how much saving you could make.
Great. I have a question, which is the role of the software in the semiconductor industry. And the other question is, what's your, let's say, what do you think about the investing in this industry, for example, in Iraq? Is it in the manufacturing side, or in the design side, or in the application side, which is mainly rely on the software? So let's start with the first question: is the role of software in this industry, please?
Yes, I mean, the software is everywhere. I did not really focus on that in my presentation, but I have to tell you, that we don't design microchips, using any software. No, we spend millions and millions on software in every step of the architecture, of the design, of the layout, of the synthesis, of the testing, DFT, design for testability, etc. And it's all software, all simulation, timing closure, power analysis, IR drop, crosstalk, noise cancelling, modeling, fast speed, you name it. These are all different software, different tools. Mm-hmm. I just mentioned it as EDA, electronic design automation. And that's because the focus on my talk was on the hardware, not on the software. But the software plays a huge part, in this industry. Add to that, you've got the board, you've got the processor. What do you do with it? You have to boot it up, right? You have to have some assembly language and machine language in order to make use of it.
True. I think we are now came to the end of this webinar. I don't think so there is any more question, just maybe last question from Bashar, sorry. It is the main issue. What's the main issues coming from the manufacturing process? It's a quite big
manufacturing
question.
Process. They all compete to have.
Okay.
They all compete to have faster processor, smaller, and lower power. So these are the three factors. But they are the shrinking factor, which is coming like from a large transistor to smaller. They are not reaching the limit, but the shrinking factor is slowing down because it's becoming very, very expensive to go. They use for this printing, UV, it's ultraviolet, but they are reaching the limit of the wavelength of the ultraviolet. So they invented a new version of ultraviolet, I think EUV, and in order to get to finer geometries. And the other thing is that they are increasing the number of layers and so on. So it becomes really, really expensive. If you want to do one chip, it will cost you like probably $20 million in order to make one. But if you make 100 millions of them, then the price will come down maybe $3. So the initial cost is huge. With the advanced technology, it's becoming more expensive, very expensive.
So the second part, Dr. Ala, what's your, let's say, what do you think in terms of investing in this technology in Iraq? Is it in the manufacturing level, or in the design level, or in the application level? Because, yeah, I mean, in Iraq, in this industry, Dr. I think Ali Sharbaz, he mentioned about the Al-Mansour company in Iraq, which used to be there. I don't know if it is still there or not, still working or not.
I don't know about Al-Mansour. I mean, I know that in the late 70s, yeah, Iraq had the Science and Scientific Research Council, or Majlis al-Bahth al-Ilmi. And one of the centers was the Electronic and Computer Center. And I knew, the head of that institution was head of department when I did the university degree in Iraq. And they were doing, you know, some good research and so on. But since I left Iraq, I don't know whether there is something equivalent to that. Back to your question about where to start, I don't think we could start with the manufacturing, because it's very, it requires very high capital, very long-term investment before we could reap the benefit. So we could do what the Indians have done. They focus on the design. They created some very good talented people, and that played a pivotal role in the design of electronic circuits or integrated circuits globally. A lot of companies they have in Hyderabad and Bangalore, it's like Silicon Valley, but the Indian are not advertising, like it's not well known and so on. But in these two places in India, there are hundreds of thousands of qualified, you know, talented engineers.
I agree with you, especially with the investing in a big project. It needs a management, and this is what we are have a lack in Iraq actually in this sector. So maybe investing in the design or maybe applications of using these semiconductors and electronics and ICs, it could be a more successful in Iraq than investing in the manufacturing at this stage.
Yeah, we might focus on you know, what the southeastern countries, South Asia, assembly and test, for example, because the capital is not huge, and you could create that gradually, and then you go to manufacturers and IDM companies and so on. You say, okay, we offer you this service, but you have to be very knowledgeable. You have to be world-class knowledge, engineers and talent. You know what you're talking about, and you present yourself as a credible player in that small, you know, segment of the industry.
Yeah, I think we cover all the questions, and definitely, please, if you have any further question, you can contact al-kindi via info@alkindisociety.org, or contact Dr. Ala. We can share his contact details if you want to contact us. Also, I would like to thank Dr. Ala for his presentation that gave us a glance about the semiconductor industry, which is excellent presentation. Also, I sincerely appreciate your attending this webinar, and I wish you to enjoy the rest of the evening, and hope to see every one of you in the next event of al-Kindi Society.
I think Dr. Ali Sharbaz raised hand.
Oh, sorry, Dr. Ali Sharbaz.
No, sorry, this is not. I'm not raising my hand. Just clapping to.
Right. Okay. Thank you.
Thank you very much.
Thanks. Thanks very much.
Thank you.
Okay,
everyone.
I hope you enjoyed it, guys, and you benefited from it. What I would like to say now is my slides will be on the al-Kindi Society website. So yeah, and maybe tomorrow. I don't know how long it takes, but I'll make it available for anybody to have a look.
Thank you very much
in future. Well, thank you for attendance, and I hope it was you found it useful.